Yes, we have no bolts, at least not at this time. Last night, the NTSB gave a good presentation full of a lot of information as to the latest on the Alaska Airlines Flight 1282 loss of their door plug, which occurred back on Friday, the 5th of January. Let's check it out. My name's Juan Brown. You're watching the Blanco Lirio channel. This is the third in a series of videos about this particular incident. It's best if you watch each of these videos in a series to keep up as to what I'm talking about. But I will review, for those that are just joining us now, what's going on with this investigation. Then we'll go over what the NTSB discussed last night, and we'll go back and review some of the prior maintenance history on this aircraft and look at some of the factors that the crew was facing in this very short 20-minute emergency flight. On Friday night, the 5th of January, Alaska Airlines Flight 1282 departed Portland, Oregon for Ontario, California in their brand new 737 Max-9 aircraft, which they just received from Boeing back in October. Climbing through about 14,000 feet or so, this plug door located on the left side of the fuselage behind the wing departed the aircraft, resulting in an explosive depressurization and a severe emergency that the flight crew had to deal with. They safely got back on the ground just 20 minutes after they took off. So what's a plug door? A plug door is a plug plugging an emergency exit that may be used at a later time if they stuff in so many seats into a sardine-like configuration of the 737 MAX-9 that would require an additional emergency exit. Remember, there's the requirement, as we learned in the Haneda accident, to evacuate all the people on board the aircraft in a matter of 90 seconds using only half of the available emergency exits. So once you get the capacity of the 737 up to so many passengers, you have to replace this plug door with an actual operational emergency exit. In the meantime, you just work with this plug door, which is supposed to be simply bolted into the airframe so that it remains in the airframe. And there's 4 bolts that make this happen. And right now, the investigation cannot find these 4 bolts that were supposed to keep this door from rattling around and leaving the aircraft. The specific bolts in question are these castellated nut and cotter key assemblies. At least that's what we call them here in the States. And on the bottom of the door, these 2 bolts are located on this hinge guide right here. And at the top of the door, here at the track guide fitting, are 2 more bolts that pin the track guide fitting onto the roller pin located right here. Again, this is the door frame, and this is the door itself. Now, that the torque on these bolts right here is not as critical as some bolts located in the rest of the assembly that we'll talk about in a minute. Again, these are just castellated nuts and a cotter key that act as a pin just to keep things from moving. The whole idea of this door is that you have to lift it vertically in order to clear the stop pad, which is bolted to the door frame, from the stop fitting, which is part of the door. This whole assembly needs to come up about 1.5 inches before those 2 stop fittings can clear each other, and that's what creates the plug style of this door, where the pressurization from inside the cabin pushes the stop fitting against the stop pad and holds the door in place. So you lift that up about 1.5 inches, then you can open up the door. And that's apparently how this door failed, and apparently because of a lack of these pin type bolts right here, 4 of them. Now, the NTSB's got the door. The door looks to be in excellent shape. They are shipping it back to the NTSB facility in Washington, D.C., and they will easily, with their electronic microscopes, be able to look into these various holes where the bolts should have been and determine if there's any witness marks to some kind of a witness of a bolt failing in this position, or if the bolt was even ever there at all. It was also mentioned in last night's NTSB briefing that this track guide fitting was found in a cracked condition, but that it was cracked as a result of the door departing the aircraft, not the cause of the door departing the aircraft. Here's a look at the larger assembly. Here's the track guides up here where the top two bolts need to be located, and here's the hinges down here at the bottom of the door where the bottom two bolts need to be located to keep this door from moving vertically. And here are the 6 on each side stop pads which engage with the 6 stop fittings on the door, which holds the door in place while the door is pressurized. There are no bolts going through these fittings here. Now, the FAA has grounded the affected airplanes, the 737 Max-9, with these plug-type doors, and what's disturbing is during these inspection of these airplanes to comply with the FAA emergency AD, which is still being written as we speak, operators are finding these bolts okay, but they're also finding these bolts that attach the guide fitting onto the door as being loose. These bolts here have to be torqued down to a prescribed torque value. Much more critical on the torque of these bolts than these pin-type cotter-keyed castellated nut bolt arrangements. And in the NTSB briefing last night, they found all of the rest of the parts of the door plug assembly, but what they are still missing is these springs. It's because the door just launched off of these hinges. The springs were free to fly if there was no bolts here pinning the whole thing together. And also, they're missing one of these hinge fittings, one of these zinc chromate green hinge fittings. And that is important to me because that seems to indicate that maybe this hinge fitting, these bolts failed as well, causing this hinge fitting to fall off of the door itself. Now, at last night's NTSB briefing, there was a good breakdown of the flight data recorder summary for the aircraft. By the way, the cockpit voice recorder was apparently overwritten, losing all the cockpit voice recorder data. Now, about that. At the end of the checklist, at the end of the emergency landing checklist, there is a small mention of consider pulling the circuit breakers after this emergency. This flight crew had gone through a very traumatic emergency situation. In fact, it was so traumatic, we'll talk about the cockpit door and all that in a minute, but a lot of their checklists got blown right out of the cockpit. I believe you're going to find out that this crew had to do a lot of this initially from memory. By the time they got this heap on the ground, they were done. They'd had it. And so pulling the circuit breakers, I give them a pass on forgetting to pull the circuit breakers. But what I'm not giving a pass to is the maintenance management at Alaska Airlines. Somebody along the line should have thought or had a checklist that says to remind you to check to see, has anybody pulled the cockpit voice circuit breakers to make sure that you preserve that data, because after so many hours, that data will be overwritten by new data. So that cockpit voice recorders were lost, but that's okay. In this particular case, I mean, it would be a good human factors study to see exactly how this played out. But everybody made it, and the crew is there to tell their story, and the flight data recorder tells the story, and the whole thing was over in less than 20 minutes. So the aircraft took off at 5:06 local time, and just 6 minutes later at 5:12:33, the cabin pressure went from 14.09 psi to 11.6 psi, and that was at 14,830 feet. And if you look at the FlightAware data here, what I like about FlightAware is they preserve this weather information as well. And it looks to me like they're just about to go into some weather. So I suspect they're starting to get some turbulence. So at that same point, they get the cabin altitude warning of the cabin altitude going above 10,000 feet. Then at 17:12:34, 1 second later, the master caution comes on and the cabin pressure drops all the way down to 9.08 psi. That is basically atmospheric pressure at that altitude, 14,850 feet. So what it appears to me is that this door, as we discussed on the previous video, it's set up like a mousetrap setup, just ready to depart the aircraft. It's just hanging by a thread, and you get some turbulence and something just cracks that door open briefly to allow that first 1 second escape of air pressure from the inside of the aircraft, the air pressure begins to drop, and now you have less pressure pushing that plug type door against the stop fittings. And if you hit another bump door, that's what allows the door to lose that last little bit of contact with the pins and escape from the aircraft. Now the aircraft continues to climb. The aircraft is on autopilot. Aviate, navigate, communicate. The first thing the crew needs to do at this time is they are now faced with an explosive depressurization. There's massive chaos in the cockpit. The cockpit door is blown all the way open. Their headsets are blown off the top of their heads. The quick reaction checklist, I believe it is blown out of their hands. And the most important thing in a rapid depressurization now is to save yourself. You got to get your oxygen mask on, 100% oxygen, and communications established. Now, this isn't such a high altitude that it's that critical here at 14,000 feet. They've got plenty of time of useful consciousness. But in all this chaos of getting this oxygen mask on and the communications established, and you got to reset the audio panel and turn up the speakers, and you can't hear a damn thing because it's so damn windy out there, it takes the crew about a minute to get this together. And then about a minute after the depressurization takes place, they begin to level off and descend the aircraft. So just about 1 minute after the explosive depressurization, the climb tops out at 16,320 feet. Again, with the autopilot and the airplane climbing, these airplanes climb very fast. The climb tops out at 16,320 feet, and then a few seconds later, the altitude in the autopilot is set from 23,000 feet back down to 10,000 feet. And then 14 minutes later, the crew is back on the ground at Portland. They did an excellent job. If you listen to VAS Aviation ATC audio, you'll hear the captain having to holler through that oxygen mask. They take charge of the situation. They keep the autopilot on, which is a common procedure in rapid depressurizations and emergency descents. You set the altitude to 10,000 feet so you don't hit any rocks that are down below you in case you, the pilot, are incapacitated. They go ahead and take it upon themselves to get themselves established on the approach, the localizer back to runway 28, I think left it is there at Portland, and get themselves back on the ground in a timely fashion. Meanwhile, ATC controllers were a little bit baffled about the whole thing and asking a whole lot of questions along the way, but that's where Mayday, 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 or the declaration of your emergency can hopefully clear that up sooner. Now let's talk about the prior maintenance history on this aircraft. As reported in the news, there was a repeat write-up of the automatic portion of the pressurization controller to this aircraft. In all these 737s, this is a picture of an older controller here versus the Max controller, but it's still basically the same setup. In all of these aircraft, for redundancy, the pressurization controller has two computers. Each time in the 737 you take off, the computer selects the other controller. So they're constantly going back and forth between the two controllers on each takeoff. If there is a problem with the pressurization controller that you are currently on, the system will automatically switch over to the other pressurization controller, and it'll give you an auto fail light. Now, you are still working on the automatic pressurization controller, you're just working on the other one. If you flip this switch over to alternate, you'll get rid of that auto fail light. Now, if both pressurization controllers fail, you can always go to manual and just manually control the pressurization like you used to do as a flight engineer on the 727. And you manually control the outflow valve using this switch here to keep the cabin pressure differential within limits and to keep the cabin climb and descent within limits. Now, when you have a repeat maintenance write-up, the airplane is talking to you. It's trying to tell you that something's up. And there's a laundry list of things that will cause the auto fail light to come on with the pressurization controller. One is if the cabin altitude exceeds 13,875 feet, or the cabin rate of climb or descent exceeds a preset value, or if you lose AC power, or if you lose DC power, or if the differential pressure exceeds a certain amount, or if you have some other fault in the pressurization controller. So generally, when these faults occur, we usually think, it's a problem with the controller itself. But in this case, I bet you that door was leaking and causing one of these triggers to trigger the auto fail light in this automatic pressurization system. And remember too, the door open light on these plug doors is deactivated because the plug door is supposed to be bolted shut. So there would be no maintenance history of the SPSEU coming on for the plug door. Okay, so how can you keep flying this airplane if you've got a known mechanical problem with it? Airliners are built with an extreme amount of redundancy. There's often 2 or 3 systems to cover one single operation. And so there's a separate document called a MEL, or Minimum Equipment List, that's approved by the FAA that tells you exactly the number of redundant systems that you need to have available before you can dispatch the aircraft. And in many cases, if you have a system that has 3 redundant systems, you can dispatch the aircraft with one of them unavailable or in op. And there's usually some caveats and some considerations that you got to do: add more fuel, change some weight and balance to the given MEL, but that's why you got to reference the MEL each time you have one of these write-ups. And it's clearly written in the logbook with a number on it as to what MEL item applies to that airplane at that time. Now, regarding ETOPS, or extended twin engine operations, these 737 MAXs are capable of, and they do frequently fly from the West Coast to Hawaii and back. And that Hawaii run is one of the longest ETOPS routes without a suitable alternate airport that you can fly on the planet. And one of the many ways you can identify that your aircraft is ETOPS certified is it's written right here on the nose gear door. Ask me how I know. Now, when you have an MEL write-up of an inoperative system on your aircraft, you need to read the fine print in that MEL and see if you're going on an ETOPS flight, if you're going to Hawaii, is this MEL item allowed for ETOPS operation? And oftentimes, things like a in-op pressurization controller can, in fact, still be allowed to be used on an ETOPS flight. Why? Because every ETOPS flight is fuel planned for that given scenario, worst case scenario of getting to your equal time point, not the midway point geographically, but equal time point based on the winds, having either A, an engine failure, or B, a depressurization, or C, both, requiring you to descend to a much lower altitude. In the case of a depressurization, you got to go all the way down to 10,000 feet and continue the flight at that lower altitude, at that much higher fuel burn at that lower altitude. So you've always got enough excess fuel on board these Hawaii flights in order to handle that worst case scenario contingency. But according to last night's NTSB report, Alaska Airlines said because it was a repeat write-up, that's why they took it off of ETOPS operations, not because it was allowed or not allowed by the minimum equipment list. So that brings up the question that, well, as crew members, when you see these repeat write-ups, every time you go into the cockpit in the airplane before the flight, you pick up the logbook and you look through it, or nowadays electronically, you can look at it ahead of time on your iPad and look at the history, the write-up history in these aircraft. If you see something that has been written up multiple times, you as the captain, the pilot in command, or even as the first officer, you can refuse to take that aircraft if you are not comfortable with the repeat write-up nature of this maintenance situation. And the union, the pilots union, will back you up on this. So you do not always have to be compelled to take an aircraft if there is a repeat maintenance write-up that you're not comfortable with. You're going to have to answer a few phone calls about it, but you always reserve that right. Then something else came up in last night's NTSB briefing that's kind of got me concerned. The cockpit door. It was brought up in the briefing that the crew was surprised to learn that the cockpit door is designed to pop open in the event of an explosive depressurization. And I agree. I never have seen in the manual where the cockpit doors are designed to open up in an explosive depressurization. What we've been taught as pilots is that since these doors were modified after 9/11 and hardened, that these blowout panels that you see here is what is supposed to allow the equalization of pressure between the cockpit and the cabin. And it's very important that that happens. You have to keep the cabin equal throughout the cabin, regardless of where the depressurization is. If it's in the cabin or up there in the cockpit, you got to keep that equal. And these blowout doors were always supposed to handle the load. But now we're finding out that the cockpit door is supposed to swing wide open in the event of an explosive depressurization. Well, that's news to me too. And that begs the question, well, what else did Boeing leave out of the manual on the 737 MAX? Because this is what got him into so much trouble, this omission of information in the pilot's manual with the 737 MAX and the MCAS system. All in an effort to not stir up a controversy with the FAA regarding the common type certificate rating of the aircraft, in order for the 737 to keep the same type certificate rating as all of the other 737s. That is a slippery slope. So additional omissions discovered in the 737 MAX manual regarding the cockpit doors and explosive depressurizations. Additional loose bolts being discovered in subsequent inspections of the entire door plug assembly, and a multi-operator message sent out back in late December regarding loose bolts found in the rudder assembly. Boeing has asked airlines operating the 737 MAX to inspect specific tie rods that control rudder movement for possible loose hardware. One of the airline operators deploying the MAX has reportedly found a bolt with a missing nut when performing routine maintenance on a mechanism in the rudder control linkage. What else do we got to worry about on these new aircraft? Thank you so much for your support of this channel, especially the folks over on Patreon that make this content possible. See you here.